Okay, so hello everyone. Our start lecture today will be on pseudorandom generators for the stream Cipher encryption. And let me move to my brilliant whiteboard. And this, okay, yeah, it seems to be in focus. Okay, so let's see if it's really in focus. Last time, we showed that the pseudorandom generator we are Katz-Lendel around section 3.3, okay, between 3.3 and 3.4. Okay, so that's where we are in readings. So last time we showed that PRG implies an indistinguishable encryption. Namely, if G is PRG, which takes n bits and outputs takes n-bit random seed and output p-n-bit bit string, and understanding is that this is always larger, this polynomial. Then, if you encrypt like this, the encryption takes the key and a message and outputs just expansion of the key using the PRG, XORed with a message, is insecure. And the key space is n-bit strings, but the message space is p-n-bit strings. So, the understanding is that n can be 100 bits, 160 bits, 256 bits, okay, something of that nature. And P of n is megabyte, gigabyte, terabyte, okay? Okay. So far so good. But how do we find PRG? And of course, by find I mean construct. Okay. So here is what we could do. So do it in 2 steps. Step 1 is construct what I will call a small PRG, i.e. Pn is just n plus some constant c, where c is a small constant. Smallest PRG would be for this constant is 1. So basically, a really small minimal PRG takes inputs which takes just n bits, and the outputs are just 1 bit longer. So goal is for this to be a PRG, meaning that if I look at the distributions of outputs of G, where I take a uniform n-bit string, it should be computationally indistinguishable. No one can tell such formed outputs from a true uniform n plus c bit string. So here is an example, c equal 1 in this example. So like instead of asking that the output has a million bits, billion bits, trillion bits, right? Times 80, times 8, right? Could be bytes, I guess. I'm just asking that if the input has 100 bits, then maybe the output will have 100 and, how about 120? Okay, not much more, just a little more. In fact, I would be already sort of happy if I get a construction that has just 101 bits. Already that is non-trivial because I have only 100 bits of entropy, and somehow I have to spread them around onto 101 output string in such a way that somebody looking at this cannot tell it from a true string that has n plus 1 independent bits. So information theoretically, that is impossible. Like if there is only n bit of entropy, something here has to be repeatable, right? There is a space of 2 to the n plus c, all possible outputs, but the outputs of G, of G have only at most 2 to the n possibilities. So random output in here, is at least for c equal 1, at most half of the space are formed in this way, right? But how can I make it so that no efficient algorithm can distinguish inputs taken from this half and from the complement? It's a half if c is 1. Okay, so that will be step 1. Step 2, harness a small PRG to create a big PRG for arbitrarily long outputs. So let's say I have this some code which scrambles these inside bits and creates output bits in such a way that nobody can tell a pattern. Nobody can tell that these outputs are correlated. So they do belong to this partition in the n plus c among all the n plus c bit output strings. Okay, could I use this little g so that to create a G prime that has these huge outputs, and the huge outputs remain indistinguishable from huge random bit strings, i.e., for every polynomial p, construct G prime from, harness a small polynomial g to create a big PRG, let's say G prime, from G such that such that G prime is a PRG, it's a secure PRG, but G prime takes n bit strings and outputs n p of n bit strings, whereas the little guy outputted only a few bit extra. Hold on, this is not focused, right? Okay, so this part is harder. It's in KL section 7, which is called theory, more theoretical constructions. It's definitely harder to see. It's also conditional based on something called one-way function. So let's postpone this. Okay. It's the one-way function is it's a beautiful fundamental thing in crypto, that there is some functions which are easy to compute but hard to invert. Like, for example, it's easy to multiply two primes to create a composite, but if you're given a composite, there is no efficient algorithms to factorize products of two primes. So going back from the product to the factors is hard. This part actually tells you how to harness such one-way function to create an operation whose outputs look pseudo-random. It's not trivial because it's not clear where pseudo-randomness hides in an operation like taking primes and multiplying them. Okay, so this is the composite does not look random. It's not a random integer. It's not a random bit string. For example, it's an integer that is not divisible by small primes. So it's not obvious how to harness this to create pseudo-randomness, but yet it can. And it's like one of the fundamental results of cryptography that you can. We'll do the easier part because it's always better to start with easier. And actually, this not only and this actually gives you a window onto how this encryption is called string cipher. And the type of way where we take some mechanism that given n bits give us n plus c, n plus c bits for like a small, c, right? Well, we can code it in hardware. This is a small circuitry. Can we reuse it in some fashion to process this key into large bit string independent of the size of the circuitry? So the size of the circuitry, let's say, here is 100 bits, here is 200 bits, and inside here is 10,000 gates. But you run this once and you only get the 200 bits here. How do you encrypt arbitrarily long messages with this? This is the way. Okay, so what's our goal again? It's given small PRG, G which takes n bits and outputs n plus c bits, construct a big PRG, G prime, which takes O and N and outputs and I will say differently here, outputs C times P of N for any polynomial. Okay, so not for any polynomial, I will actually multiply in front by the C constant, so it's even better. Here is a construction which is not practical, but easier to say and good to see. So it's a little bit of a cheat also. Namely, assume the small PRG works for any n, i.e. it doesn't, the circuitry is not fixed. So it doesn't just, it's the first fixed circuit that given 100 bits gives you 180. So every time you run it, you get 80 bits of extra. But it's like a family of circuits. You give him 100 bits, he gives you 180. You give him 200, he gives you 280, etc. Okay. I.e., the size of the outputs of GX is always the size of X plus C, for every bit string X. Okay, it doesn't have to be an n bit, it's arbitrary number of bits, it always expands at C. Okay, so this is a little bit of a cheat. It's not a practical construction anyway. So, okay. So here's how I would, one way to do this. So G prime, which takes some n-bit seed and wants to expand it to this, huge seed, a huge output. You know what? I will actually remove this part. Okay. So because it works for arbitrary polynomial, I can that polynomial can have another factor of n, and it comes back here. Okay, but that will be a simpler notation for me. So let G prime do this. Let it run G on the input. So now this output, if the input has n bits, then input here has n bits and the output has n plus c bits, right? Well, let's run G on that output. So the input has n plus c, so the output has to have n plus 2c. So let's run G on that output, and so on. And how many times do we run G in this pyramid? P of n times. Let's call it M. Okay. Well, taken another way, alternatively, you can describe this code like this. G prime on X, well, it has some initial value which it linearizes to X, and for I 1 to M, it sets Gi as G of X I minus 1, right? And finally output Xm, okay, where M is P of n. So it's the same code, just differently represented. So you can see that the length of each value, right, is the previous one plus c for every I, right? So by induction, right, like you get that this xi is just I times c plus n. Oh, I guess I do output n here. Okay, fine. Okay, sorry. Okay, fine. N plus. Okay. What about security? So syntactically, it's correct. I just run this G in a loop, apply it to its own outputs, and I have like this G that can swallow arbitrarily sized inputs and always extends that input. The output is always C bits more than the input. Well, so security is by the following observation. Let's argue it first for m equal 2. In this case, G prime of x is G applied to the G of x. So we want to argue that distribution of outputs of G prime on a random seed is indistinguishable from a perfectly uniform string of length 2c, so n plus 2c, right? That's how long these outputs are. It's the length of the input plus twice c. Okay. We'll argue it in 2 steps. Well, so first of all, what is G prime of x? So note that this distribution is identical to, by construction of G prime, I just replace G prime with what it is, which is taking x, applying G to it, and then applying G to the result. So really, I need to argue that this distribution is indistinguishable from that one. Step 1, I will argue first that this distribution which is output of my claimed PRG, is indistinguishable from taking G to string y, where I take y from n plus c bit string. Okay, pictorially, I'm putting my x in here, and I'm outputting y, and I'm putting this y into like a bigger G output, and this is my string z. So x has n bits, y has n plus c, z has n plus 2c. Okay. I want to argue that these guys, z, that come out from this, if I put in random string, these guys look indistinguishable from random strings of n plus 2c bits. Well, let's simplify this and pretend that these intermediary strings were fully random. They are not in this construction. They are outputs of G on a true random n-bit seed. But let's pretend for a second that these y's are random. And well, if these guys were random, would this be easy to argue that these guys are pseudo-random? That's the first step. And in fact, this is easy to Okay, so that's first step. Like this is what we want to do. Step 2, okay, look at this distribution now. Is G, okay, is G of Y, if so, if Y, okay, so this is what I was talking about just a second ago. If I pretend that my intermediary bits are fully random rather than output by a G operation, would it be easy to argue that this output is pseudo-random? In other words, would that be indistinguishable from this distribution? And the answer is that this part is easy. It's immediate. From PRG property, PRG property of G, right? Because this is explicitly what the PRG property is. I'm just renaming the lengths. If I call n plus c n, then this is the new n plus c. So I'm looking at the outputs of G on new n bit strings, which are fully random, and it's by security of a PRG that the result is indistinguishable from a true uniform string of the appropriate size, right? So this is immediate from the fact that G is PRG. Good. If I knew this part also, then putting these two things together to get this is basically transitivity of indistinguishability. So hold on, how much should I, that's this part is enough, right? Because we already have this construction here. So step 1 and step 2 imply the goal. So this is the step 1 part, and this is the goal.
Professor,
yeah.
In step 1, why are we comparing G of X inside of G computational indistinguishability to G of Y? Isn't it supposed to be G prime of Y? Are we plugging it into?
No, G of X is G prime of X.
Okay,
so this
and
part
on the
is
right
G
hand,
prime of X.
but then on the right hand side, why are we plugging Y into G?
Yes, well, that's the pretense, if you will, or a kind of okay. So let me show this construction again to be clear. So I'm putting an X, which is random in n bits. I'm outputting an intermediary value Y, which I then feed into another instance of G, which outputs the string Z, right? So I have n bits here, n plus c bits here, and n plus 2c bits here.
Okay, yeah.
Right? And I'm just asking you for a second to consider a sort of a cheated construction or simplified construction, or in cryptography is called round reduced construction. So this is the real G prime. Consider simplified or round reduced G prime, which would not do this at all. Instead, taken this intermediate value at random from this distribution and fed this into G Okay, so here the input has n plus c bits, the output has n plus 2 c bits, so at least syntactically it's the same. And this claim says that the outputs from the real G prime are indistinguishable from the outputs of the round reduced G prime, from the simplified G prime. You're right that in reality this is not happening, but this will be helpful in arguing that this is secure. Let's consider this simplified construction and argue that the real G prime outputs are indistinguishable from outputs of the simplified one. Let's believe that this is true for a second, right? We'll come back, like how to argue this. Let's first argue that this will be useful to know. And this will actually explain why I'm doing this. It is the case that this holds. Namely, if I knew this and that, then I can conclude this. It's more generally, if some distribution 1 is indistinguishable from distribution 2. In this example, D1 is G of X for uniform n-bit strings. So this is the real G prime outputs, which is the same as just G prime outputs. And D2 is this cheated or simplified. So G of Y for Y, which is a random n plus c bit string. If I knew this, and I knew that D2 is indistinguishable from D3, in my case, D3 is just uniform 2c bits, n plus 2c bits, then it follows that D1 is indistinguishable from D3. And that was my goal, which is the goal. If I instantiated with this, right, to show that D1 is indistinguishable from D3 is to show that G prime outputs are indistinguishable from truly random bit strings of length n plus 2c. So that's what I wanted. This is what I would get from step 1. This is what I would get from step 2. And I'm claiming that this works in general. So let me quickly sketch why this works in general. Because if there exists an efficient algorithm that distinguishes D1 from D3 with some advantage epsilon, and this advantage is epsilon is not negligible, then the efficient algorithm, let's call it A, then A must either distinguish D1 from D2 with advantage at least half of the epsilon, or he must distinguish D2 from D3 with advantage epsilon over half. And since epsilon over 2 is not negligible, if epsilon is not negligible, claim follows. Okay, so technicality. If epsilon is not negligible, then so is epsilon, half of the epsilon. This is exactly like in the homework. In the homework, you're asked, if you have a negligible function and you multiply it by any constant, you also get a negligible function. So basically multiplying functions by constants, keeps you in the same. If you were negligible, after multiplying by constant, you remain negligible. If you are not negligible, then multiplying by constant moves you to not negligible, right? Because you're just a constant away. So you cannot move between these two classes, right? The homework asks you to prove. If you have a negligible function, multiplying it by any constant moves you, the new function is still negligible. So this claim in particular will follow. Now, if you believe that, okay, if there's some function that vanishes fast, then okay, that does not vanish fast, right? Like it's upper bounded by some polynomial, 1 over some polynomial. Then dividing it by 2, it's still upper bounded by some polynomial. What polynomial? Well, the original one divided by 2, and that's still a polynomial, right? Or multiplied by 2. Okay. Okay. Now this claim follows because the assumption was that there is no efficient adversary who distinguishes these two, and there is no efficient attacker that distinguishes these two. So it's a proof by contradiction. Assume that the statement is not true, meaning these two do not imply that. Okay, so you can have a situation where there is no attack that distinguishes these and no attack that distinguishes these, but there is somehow an attack that distinguishes these. And this is not so, shows that that's not so. If there is an attack that distinguishes these, this same attack will either distinguish these two or distinguish these two and therefore violate the premise. Okay, so this is proved by counterpositive, but I actually haven't proved that yet, right? I'm just saying this is true, but this argument is well, it goes like this. Let P1 be the probability. This is the probability that A outputs 1 on input in D1. So he claims to distinguish D1 from D3. It is the proof by contradiction step. Let's assume that there is an algorithm that can distinguish them. So there is some probability with which he outputs 1 given input from D1. And here is some probability P3 that A outputs 1 on input in D3. Well, of course, what I'm going to do is to consider where can P2 be? Where P2 is the probability A outputs 1 on input in D2. And if the distance between these two is epsilon, by the assumption that A distinguishes D1 from D3 without advantage epsilon. In other words, A is some machine that given inputs from D1 outputs 1 with some probability, given inputs from D3 from some other probability, outputs 1 with another probability, and the difference between these two is at least epsilon. Well, then it has to be that either this distance is larger than epsilon half, or this one is larger by epsilon half, right? You cannot get from point 1 to point 3 passing P2 and makes you just 2 steps, both of them are less than half of this. You cannot get from here to here in that way, right? So either this step has epsilon2 or more, or this one. They cannot both have less. And that's exactly what this says and this says, right? If this distance is larger than epsilon half, that's what this says. And if this distance is larger than epsilon half, that's what this says. So that's the end of the proof. Know why this is true. Okay, that indistinguishability is transitive. If I cannot distinguish these 2 random variables, and I cannot distinguish the first variable from the second, and also the second from the third, then I cannot distinguish the first from the third. Okay, and that is exactly why it is helpful. It is helpful to consider here we are trying to argue that running G twice outputs a string that is indistinguishable from truly random. Well, let's consider an intermediary distribution. It's not the full construction, but it's not a fully random string either. It's in between. It's this one with first round cutoff and just pretending that this intermediary values were truly random. If now, so this is the D1 distribution I have. This is the D2, and the D3, which I didn't draw. I just take Z with nothing, so just complete, random from the prescribed range. That these 2 are indistinguishable, that this is part, and this just follows immediately from security of a PRG. If I can argue this claim that these 2 are indistinguishable, I'm done. I will have that D1 is different from D3, and therefore I'm done, right? So let's look at how this is done still. So what remains is arguing this claim. Step 1 argument. The argument is that if G is PRG, then doing the real G prime construction is indistinguishable from doing this round reduced, cheated, simplified construction. Okay. But let's do something more general. It's actually in some sense easier. If 2 distributions are indistinguishable and P is some efficient algorithm, and I'm going to call it P because it's convenient to think of it as post-processing. Then the following 2 distributions are indistinguishable. If I apply this post-processing to an input that comes from the first distribution, that must be indistinguishable to outputs of post-processing applied to inputs that came from this second distribution. So think intuitively. If no efficient algorithm can tell inputs that are sourced from here, from inputs that are sourced from here, then it doesn't matter how you post-process these inputs. So you source the inputs from this distribution, or you source from that one, but then you apply this post-processing to them. The post-processing cannot help in distinguishing between where the input came from. If adversary can see post-processed inputs from this D1, in other words, you source X from D1 and then you apply this post-processing to M. Think of this post-processing as some efficient algorithm, like he chooses some fraction of the bits and I don't know, XORs all the remaining ones together, and then that post-processing cannot help in distinguishing between inputs from D1 and inputs from D2. The proof is exactly like this intuition. If there exists efficient algorithm A that distinguishes let's call this distribution Y1 and let's call this distribution Y2. Distributions Y1 and Y2 with advantage epsilon, non-negligible, then there exists an efficient algorithm A prime that distinguishes D1 and D2 with the same advantage exactly. This one is called the reduction. And it's very simple. So assume that there exists an adversary A that can distinguish things formed this way from things formed that way. I'll create this A prime that distinguishes things from this way from things from that way. If he has some input, and the question is, his question is X from D1 or is X from D2? He doesn't know, but what he's gonna do is he's going to give a string Y, which is post-process X, to A, the A who claims to see the difference between these two, and whatever this guy outputs, this guy just copies. In other words, output of A prime on X is an output of A on string Y, which is P of X. Okay, so whatever this guy, whatever his judgment about where this distribution came from, this guy just copies. And note that probability that A prime on X outputs 1 if X is sourced from D1, well, it's exactly the same as the probability that A on P of X outputs 1 if X is in D1. Right? Because, well, if X is really from D1, then what does A see? He sees precisely this distribution. Some value is chosen from D1 and then post-processing is applied to it. Likewise, probability of A of X on, that it outputs 1 for X taken from the second distribution, well, that's the same as the probability that A on post-process X outputs 1 if X is taken from the second distribution. Right, it's the same argument. So the difference between these two is the same as the difference between these two. The difference between them you know, they're away by epsilon, by assumption that A exists. So if A distinguishes this type of distribution from this with advantage epsilon, so that's what it means, that this probability and this probability are different by epsilon. So this one has to be also away by epsilon, right? Because these two is the difference between these two is identical to the difference between these two. Oh, you know, sorry. So yes, Vashi, you just have to speak up because like I don't see, sorry about not moving paper up, but you have to say it because when I write, I cannot look at the chat at the same time. Okay. Okay, so all of this was to argue this this general claim. Why is this general claim useful to us? Well, so a general claim, I will mark it with a star, and the specific thing that we want, I'll mark it with a double star. And double star is a case of a single star thing. What is the case? P is post-processing is just applying G. So in both cases, I'm post-processing with G. So this is my post-processing. And what is the underlying distributions to which I both post-process with an application of G? Well, the first distribution is like this. So D1 is outputs of G of X for random n with string X, right? You can see that this thing can be looked at as I apply this G post-processing to this distribution. Whereas this thing is applying the G post-processing to what? To just a uniform random string of length n plus c. And the fact that these two are indistinguishable, right, which is something we had to assume, right? So we needed to assume that D1 is indistinguishable from D2 to make this conclusion. Well, but what is this? This is just means that this is indistinguishable from that, you know, but that follows from PRG property of G, right? Because this is exactly the PRG property that outputs of G are indistinguishable from random strings. Okay. This argument maybe took me a while, but if you wrap it back, well, what we needed to know that these D1 and D3 are indistinguishable. We did it step by step, showing these two are, and showing these two are, and showing a general transitivity law, which will be reused again and again. So now this indistinguishability is immediate from a PRG property. this one turns out to be a case of a more general thing, which is also good to know, that indistinguishability is robust to any post-processing. And that's why, basically visually you can see, if it is the case that strings, that these intermediary strings, because of the PRG property, are indistinguishable from truly random, then in this distribution and in this distribution, they'd only differ by the choice of this y. After the y is chosen, whether in this form or in this form, the rest is the same. I apply the same g to y in both pictures. So it would immediately follow that these two are indistinguishable if the inputs were indistinguishable. That's simply what this says. If you have some procedure, then if you cannot, nobody can tell between inputs of this procedure taken from this here to there, then also nobody can tell between their outputs. Okay, that's just wrapping this argument back. If you, okay, so I only argued this for this, assuming that there's only 2 rounds. But you can see that the same argument, basically, I can repeat this argument because G of x's are indistinguishable from random by the very definition of what a G is. Now I argued that if you put it twice, then if you apply G to its own outputs, the outputs are still indistinguishable. Running this again is basically the case of the previous one, but just slightly modified. I'm applying G not to itself, but to some other PRG. This other PRG, let's think of what happens at step M. Do you have some PRG inside that you already argued is a PRG, and now you apply a PRG to its output? That's a case of just some PRG run first and then some PRG applied to that. It just happens that in our case, case M equal 2, this inner PRG and the outer PRG were the same algorithm, but this is not needed anywhere in this argument, right? Like the inner one is this guy, the outer one is this guy. They really don't need to be the same. And that's how this argument generalizes so that you can do it at every step of this transition. It's really the same argument, just run in a loop. And at the end, rather than just arguing that 2 from here to here and from here to here implies this, I will have M distributions, the real, and then one with the first round removed, and then one with the 2 rounds removed, to the last one, which does look like this, with all rounds removed, and just choose the final bit string at random. At every step, I will have a case of this. Some PRG outputs this, or I just cut it out and put a random string in it, and some post-processing, which is the remaining rounds of this recursive construction. And it doesn't matter. At each step, I can do the same argument. And now I will need final transitivity. That okay, I argued that the transitivity works if it takes 2 steps. But if it takes M steps, it doesn't really matter. The only if I have more PM rather, then okay, I still cannot cover this path unless at some transition I move by epsilon over m. Since m is polynomial and epsilon is not negligible, defining non-negligible polynomial still keeps you in a non-negligible class. And so that's the same exercises in the homework. Okay, so it's like a little bit sketchy why this argument generalizes to the full you know, arbitrary number of this G applications. But hopefully this intuition suffices. Now, why it's not practical? Well, not practical because G has to run on larger and larger inputs. And however you construct G, it will have to work in some times that is related to the input size. So, you know, at best, you know, the best case, G of X runs in time linear, right? It has to swallow all inputs and do something with them. So let's say that it's somehow linearly in the size. But G prime on, so say it works, okay, like C times X time steps. So G will take how many? C times X, well, not C, because I already used that value, like A, okay? Or you know what? Let's just take the easiest linear function, just the input itself. So this many steps to first round, first execution of G. The next execution runs on X plus C string, right? The next one, so this is the second. The next one on X plus 2C. And so on, right? What was the total time? M times X. And how many times this? M squared. Yes, because C, 2C, 3C, etc. to MC. Well, this is going to be a sum. So it's like this. So if M is, you know, say gigabyte. Okay, so you know, 10 to the 9. I guess if n is let's say 2 to the 8, okay, you know, 2 to the what? 256 is 2 to the 8, yeah. So 2 to the 56 bits. And so gigabyte would mean 2 to the 32 divided by 2 to the 8, right? Because at every time you create, okay. So let's say C is so 2 to the 8. Okay, so you take the input and you every time you add 256 bits. So if I want 2 to the 32 bits in the end, which is a gigabyte, I guess is 2 to the 30. Then I have to run this whole thing in a loop divided by how many bits all I get in one chunk, right? So that's 2 to the 22. But M squared is 2 to the 44. right? So that's a lot. Yes, so it's basically does not act nice at all. I mean, it's intuitive, I think, that if you are running something that basically, you know, grows like this, every time you output this, you have to process this again to create this new intermediate thing, and you have to process this whole thing again to create this, and you have to process this whole thing again to create that. Okay, so that's going to be quadratic in the number of rounds of this thing. So quadratic processing. Okay, because, you know, yes, you have m rounds, but if each of them is just linear in its input, right? The inputs grow by, you know, the average input length here is half of m, and you're doing it m times. Okay. So I will just show you what the real things do, and the proof is a little more complex, but not really, but we're going to skip it. And you can, you know, see in some lecture if you want online. Construction 2, the practical and, you know, really used. There's this. So G prime on input X sets the initial state to X as before, and then sets the new state and outputs bits, and it sets yi to 0, to an empty string. Y0, sorry. For I equal 1 to m, it does xi yi as g of xi minus 1, where the parsing of this is that this is n bits, and this is this extra c bits. So G takes n bits and outputs n plus c bits. Okay, so if the input here is n bits, then I can parse the output as first take the n bits, call it the new x. The remaining c bits, call it yi. Run this in a loop m times, and output y, which is the concatenation of all these yi's. Y1, Y2, so actually I don't need this. Y3 to ym. This whole thing has c times m bits. So G prime takes an n-bit string and outputs a c times m bit string, and claim G prime is a PRG for any polynomial p for m equal p of n for any polynomial p. Okay, so if I instantiate this construction with m, which is an arbitrary polynomial of the security parameter, which is the length of the seed, then I can do this safely. And all my outputs together are indistinguishable from a random string. And that's provided that if G is a PRG. What's the difference between these two constructions? You know, kind of a tiny difference, but the difference, but that tiny difference matters a lot in practice. Where is this code for the other one? The G construction one, right? It set the seed like the same way at the beginning, but treated the whole output as the new seed. Whereas this guy only takes the first n bits as the new seed and saves the c bits, the c extra bits of the output, and uses that as an output of the whole construction, right? Rather than the seed that grows and grows and grows. Pictorially, this means that I can now use a short circuitry. So this is x0, which is x. It outputs x1, and it outputs y1. And it's divided here. This is the first n bits, and this is the n bits, and this is the c bits. And so I feed this again into my G. And I parse the input again. This is the y2, and this is the x2. And I recurse. This is my last xm, which I don't use, ym, which I do. And this is my output. So this is the G prime output on input x. I don't have the quadratic issue anymore. Whatever cost of processing n bits using this PRG, small PRG construction is, the whole thing runs it, whatever the cost is, because it's the same in all instances, times m. So it's linear in the m, in the length of this output, which is what you would expect. I want to produce 2 megabytes of this stuff at roughly the same time, you know, twice the time that it takes me to produce 1 megabyte. And that's the case here. It will be exactly the case. Like it just runs the same code, just twice more to produce the twice larger string, you know, right? Why else this is useful? Because basically I can also look at this like this. So x0 is x, and I feed this xi, and I get the new state and the output. So this is my my G prime construction, which has this small circuitry of G inside and just updates this local state variable and spits out pieces of the string. And that's a very useful usage of the PRG, because recall how PRG is used in stream Cipher. Okay, and that's the last thing I will say. I know I'm going over time now. So encryption of a message under a key is the output of this. So how PRG is used in the stream Cipher, but now I will use stream Cipher G prime. Right, the G prime will be the stream Cipher that I want, that outputs huge strings that will let me encrypt huge files. Inside of the G prime, there is a little g. So the encryption outputs G prime XOR M. If M is subdivided into chunks like this, M1, M2, and each of them C bit long, which is natural. Data sources occur in some chunks. Like these could be like disk segments, or whatever chunks of transmission that you're processing by encrypting it. Then if this thing comes in chunks, and it does using this construction, y1, y2, ... That's very convenient, because what do I do to encrypt? I encrypt y1 XORed m1, and that's my first part of the ciphertext, and then y2 XORed m2. So here is the benefit. I don't even need to know what's coming. I only need to know the current disk drive segment that I'm encrypting. If this drive has C bits, this construction just has to spit the first C bits for me to be able to encrypt it. It will also update its state and be ready to spit out the next C bits. So when I move to the second segment of the drive, and this has C bits, I press the button here, it spits out the next C bits. This is the y2. I use them to encrypt. This is the real usage, beautiful usage of string cipher encryption. I can process these fragments one by one. The growth of this algorithm does not depend for how far I went. Every time it jumps and spits out the next one, it just keeps a small state and is able to process, output the next segment. The same is going to work very well for transmission, right? Not in disk encryption, where in a natural way, if I'm a gateway that has some M bit stream, I'm using this Y to encrypt the C's, right? So this is the usage within the encryption application. I get like some buffer. I don't know how long it is, how long it's going to be. I just know the current C bits that is entered into the buffer. I am able to encrypt them and spit out the corresponding C bits of the ciphertext stream. Oh, okay. Okay, so sorry about going over. Do you have questions that you want to record? I can also stop recording. I'll stop recording right now.